All right, everybody. In this video, we'll be talking about um, how to approximate different solutions to differential equations by using direction fields and an algorithm to refine our solution curves a bit more. And it's by using Euler's method. So the goal of this chapter is to present methods for finding solutions of various kinds of differential equations. However, there's going to be some that will require, instead of just solving it by hand, we're going to have to visually inspect what these solution curves would look like. And this method of estimating a solution curve is by drawing in what's called a direction field, or they call it a slope field. So the idea is this: dy dt equals f of ty. This represents the slope of a tangent line passing through a point t and then y of t. Okay, so t is the independent variable and y of t is just a function depending on t. All right, so so what this says is that at each point ty of the solution curve, the slope of the tangent line at that curve is just y prime of t equals to f of ty. All right, so we have an example right here. So this is what a direction field looks like. So the idea is, for every point that is on this grid, we draw in a dashed line to indicate what the slope of the tangent line will be at the indicated point, thereby giving us an idea of what a solution curve would look like. So here's one possible solution curve that's in black. Here's another solution curve that's in red. And here's also another one that's in blue. Okay. And so this here is the example of a direction field with the differential equation y prime of t is equal to y squared times e to the minus t. All right. Now, if you notice, there are dashed lines that appear horizontal. So near at t equals 0. I don't know if you see that, but there's horizontal dashes near t equals 0. And this is a special point because at so at y equals 0, this is where the differential is what's called equilibrium. Okay, so this is where y prime of t is equal to 0. Okay, so they call these solutions equilibrium. Okay, so for its so as an illustration, if we were to look at y at the point 0 2/3, so at the point 0 2/3, t is 0 and then y is 2/3. Y prime of 0 in this case is 0 squared e to the minus 2/3, which is 0. Okay. And if I were to pick at another point, let's say 2, 1, then that derivative is equal to 2 squared times e to the minus 1, which is 4 over e. So this right here will be the slope of the tangent line at the point 2, 1. Okay, so about here. Okay. So dy dt equals f of ty indicates the slope of the tangent line passing through that point ty. Okay. So here is an example of a very special case where we can analyze a direction field more easily, okay? So if we want to sketch a direction field, let's say in the window -2, 2 by -2, 2. So this is a square whose dimensions are 2, and then 2. So -1, -2, -1, -2 here, and then 1, 2 here. Okay. Before I do that, here's the procedure to sketch a direction field by hand if we have a differential equation that looks like this. So we have a differential equation exclusively in y's, so it's not in t. So the idea is this: we want to figure out where the y values approach equilibrium. So in this case, where y prime of t is equal to 0. Okay. And this is what we called equilibrium. So y prime of t is 0. So find the y values that make the derivatives 0. And then steps 2 and 3 are basically figuring out where the y values that make the derivatives have positive values, and then the y values that will have the derivatives being negative. Okay. So that's for steps 2 and 3 respectively. Okay. So I'll show you how to do that. But first, the values that will reach equilibrium, it's where y prime of t is equal to 0. Okay. So in this case, we'll have y minus 1 times y plus 1 equals 0. So in this case, y equals 1, and then y equals -1. So what this means is if y is equal to 1 or y is equal to -1, we would have a derivative of 0. So along this grid, we will have horizontal dashed lines across 1 and a -1. Okay, just like this. Make that clear. All right, and then dashes here and then here. Okay. Next, we want to figure out where the y values are increasing in derivatives, y prime of t. So in this case, it's kind of like using the first derivative test in Calc 1. So we label the values that are at equilibrium, so y prime of t. And I'll do decreasing over here. Decreasing here. All right. So you want to draw out a number line indicating y prime of t. Next, we want to pick out specific test values for each of these subintervals, which you can't see. I'll do a different color. This here, here, and then here. So this will be like -2. Our test value here will be 0, and the third one, let's say 2. Okay. As a reminder, y prime of t is equal to y minus 1 times y plus 1. If y is equal to -2, well, we'll have -2 minus 1, which is, so y equals -2. This would mean that y prime is equal to y prime is equal to -2 minus 1 times -2 plus 1 plus 1. which is -3 times -1. That's positive 3. Since it's greater than 0, our derivatives are increasing. So it's positive, so it's increasing. When y is 0, we'll have a negative number. So in this case, -1. So our derivatives are decreasing. And when t is 2, we'll have a positive number. Positive. So in this case, when x is less than, when y is less than -1, our derivatives have a positive slope. So with values that are closer to -1, we'll have a tangent lines that have positive dashed slopes like this. And once we get closer, our dashed lines are going to get much flatter. So like this. And once we move away from -1, it will be steeper. It's like this. And like this. Okay? When we are in between -1 and +1, we have dashed lines that have negative slope. So it will look something like this. Dashed here, dash here, and then dash here. And once we get closer to the equilibrium solutions, the dashed lines will be flatter, like this. And then flatter here, 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 and then here. And then when y is greater than 2, we'll have we will have dashed lines that have positive slope. So our dashed lines will be flatter as we get near 1, and they become steeper as we move away from y equals 1. So it's steeper here, 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 and here. So the possible solution curves would look something like this. So we'll have a solution curve here. We'll have a solution curve that may look like this, that, or you may have a solution curve that looks like this. Okay. So this is a direction field. Make sense? I hope that makes sense.